We continue with the concept of memory elements. We started with a simple latch, and then we turned it into a master slave flip flop, a D flip flop, and finally we were able to write the very long description and all that, and so we have a working flip flop. And but then there is this issue of sometimes it's still good, even though we said the SR has this problem and such things and all that. But then there are times that you still want S and R, meaning that you want something to be set, something to be reset. Okay, so remember what we did before. We said, well, the set and reset doesn't look like a memory storage element. So let's put an inverter between the set and reset, and then make it a D flip flop. I'm gonna remove the inverter now and say, well, no, S and R is not a bad idea sometimes. So this is an S and R flip flop. Okay, so it is not transparent. Remember, first what we had was the transparent SNR, which is only this part here, and so that has the transparency problem. Now that it is master slave, okay, fine. It doesn't have the transparency problem, and then we have the SNR, but then there is a problem. Since we have removed that inverter, there is a possibility of S and R being one simultaneously. So what happens is, for example, if S and R become one simultaneously and clock becomes one, clock becoming one, then these two become the same, and clock becomes zero. These two, the output propagates, and then the simultaneous S and R have have caused the loss of memory. Okay, so if you like to keep this as an S and R, that's fine. We can write the transition table for it. This is SR, and this is Q plus, and with the clock, okay, with the clock, and this is the clock going from 1 to 0. When the clock goes from 1 to 0, sorry, this is the clock. Okay, going from 1 to 0, going from 1 to 0, going from 1 to 0, going from 1 to 0. If SR is 0, 0, Q plus doesn't change. 0, 1, it resets it always to 0. 1, 0, it sets it always to 1. And then that's the situation that we have to avoid, which is 1, 1 that loses the memory, and that's not a good thing. So still better than the original latch, the original SR latch, because it has the clock, it doesn't have transparency and all that, but then still has this 1-1 problem area that is right here, which we don't like. Let's see if we can resolve this issue. Let's see if we can still have something that sets and resets and is clocked and it doesn't have transparency. Okay, see, these are all good. It sets and resets. It doesn't have transparency. It has a clock. And also, let's see if we can eliminate the problem that the simultaneous 1-1 can cause. Without putting an inverter, because if you put the inverter, it's back to D flip flop, and yes, it does solve the problem, but it's no longer an SR flip flop. I'm going to talk about it this way. Look, this is the same flip-flop. Okay, don't look at these two lines, the green and the red line on the top at the bottom. This flip-flop, okay, it's either set or reset. Okay, so if it is set, this is 1 and this is 0. Okay, and if it is set, okay, for now let's say this is the set input, this is the reset input. And if it is set, the set input, there is no use for the set input, right? I mean, if it is set, that means the output is 1. What does the set input do? It sets the output to 1. But then, if it is set, it cannot be set any more than what is already set. And therefore, you shouldn't have a problem with me taking the Q bar output, which is a let me choose the proper coloring here. You shouldn't have a problem with me taking the output Q bar, which is 0, feeding it back into the gate that has the S input, right? Because Q bar is 0. Q is set. The set input cannot do anything anyway. Okay? So I'm gating it. So I actually am preventing, with this red line going across, I'm preventing the set input from doing anything. Well, it's not doing anything anyway. It can't do anything. We cannot set it anymore. Okay? I'm going to make the same exact argument for the resetting situation. Let's say that my output is reset. That means the output is 0 and the Q bar is 1. And then I say the same exact thing. I say that while I'm in this state, okay, while I am in this state, the flip-flop is reset. There is no use for the reset input anyway. So why not, or you shouldn't object to this. If I take the Q, which is 0, feed it back, bring it back, put it into the gate that the reset input is there too. And what is really happening is I'm blocking reset. I'm not allowing reset to propagate. Well, if I'm not allowing reset to propagate, what it means is that it cannot reset it. Well, no problem, because it's already reset. So I added these two lines. Now let's look at the, let's see what I'm achieving. What I am achieving is this. This is my set. This is my reset. This is my Q plus. Okay? On the clock, CLK, and this is a master slave, and I'm using this symbol for the clock. Okay? Because the way it works is after the edge of the clock, the output changes. After the falling edge of the clock, the output changes. So I'm using this symbol of the clock. The set input, if it is 0, 0, clock arrives, that's no problem at all, because Q plus doesn't change and is Q. After the edge of the clock, if set is 0, reset is 1. Again, that's no problem. Set is 0, reset is 1. I go through half into the master, and then the clocker goes to 0, and then this output becomes 0. Okay. After the edge of the clock, if my set is 1, my reset is 0, then I'm sure the output becomes 1. Now, let's see what happens if my two inputs are 1, 1. Okay? My two inputs are 1, 1. S is 1, R is 1. And now I have this green and the red line here. Okay? And now let's assume that I am in the set state. That means the presently I am 1, 1 on my set and reset, and my Q is also 1. Okay, my Q is also 1. What happens is the red line that feeds back into the S gate prevents the 1 on S to propagate through this gate here, and therefore, even though I have a 1 on S, internally I have a 0 on this internal S because of that red line being 0. See, the red line is 0 because it's coming from Q bar the time that my flip-flop is set. On the other hand, the green line is 1, right? The green line is 1 because it's coming from the Q in case it is set, and therefore this allows the reset to go through, and therefore the reset, the blue reset, now becomes a 1 here. So what do I have here? Even though externally I had 1, 1, now I have 0, 1. That means I'm only resetting it. What it means is if it's 1, 1, Q is 1, Q becomes 0. What if it is 1, 1? Now let's say Q is 0. And now let's go through the same process. 1, 1 on SNR. And Q is 0. This is 0. Q bar is 1. I am taking the green line from 0, right? Q is 0, is green. I'm taking the green line from 0, feeding it back here, bringing it into the reset case. Okay? The reset gate. Then what happens is this 0 on this feedback line doesn't let the blue one to go across, and therefore I end up with a 0 here. How about the 1 on the set input? With the 1 on the set input, nobody is preventing it from doing to go forward because the red line now is a 1, right? The red line is 1 because it's coming from Q bar. And therefore, the blue one on the set input propagates into this input here. What do I have here now? My set is 1, my reset is 0. What happens when the clock, the internal set, this is the internal set, this is the internal reset. The internal set is 1, the internal reset is 0, and therefore what happens when the clock arrives? Since set is 1, this becomes 1. All in all, what happens? What happens is my Q plus, this thing, if Q is 0 becomes 1, if Q is 1 becomes 0, and therefore this blue case is no longer a an invalid case, this is Q plus is Q bar. I corrected it. I corrected the SNR so that if 1 1 happens, this thing is not going to lose memory. Instead, what it's going to do is complement. Okay, now I have a new flip-flop. I call this one a JK flip-flop. Instead of SR, I say this is jump, this is K, this is kill. And I call this one a JK flip-flop. A JK flip-flop is the same as SR flip-flop. It has the set and reset property. 0 0, nothing changes. 0 1 resets, 1 0 sets, and 1 1 complements. Now I have created a new flip-flop called JK, and it doesn't have the set reset problem. The simultaneous 1 1 problem still is a master slave, okay? And then still is a non-transparent, still has a clock and everything else. And the clock works like we have shown before, like this. When the clock becomes 1, the input is taken halfway here. When the clock becomes 0, the D input is taking another half into the output. This is the master output, and that one is the slave output, or the actual output of the circuit. And this is the clock, and so I require a 1 and a 0. Even though we said at one point that when it comes to D flip-flop, we use the edge symbol like this, but then to be more accurate, this is how we should represent the clock. A line like this, okay, indicating that I'm getting my output right over here. We are saying this, but later on we will drop it and use that falling edge thing. All right, so what I have here is a JK flip-flop, and this is the transition table. Notice that 1 1, in the case of 1 1, Q becomes 0. If it is 1, Q becomes 1 if it is 0. Okay, so what I have is on the right hand side, I make my transition table. I remove Q, and then it becomes, if JK is 0 0, if JK is 0 0, okay, nothing changes. Okay, 0 remains 0, 1 remains 0, 1s remain 1. If it is 0 1, 0 1, 0 1, okay, it's always 0. And if it is 1 1, let's use this. And if it is, 1 0, one 0, okay, Q plus becomes 1. This is the symbol for it. And notice that I'm saying this is C1, and then C1 is controlling J and K. That means if C1 doesn't happen, J and K are ignored. Nothing happens without the clock, which is the purpose of the clock. But then the clock is shown this way to indicate that the output changes when the clock becomes 0. I'm going to take what we already have. This is the JK flip-flop, and make a different kind of flip-flop from it. Look, I'm going to wire J and K together. This is the transition table that I have, right? If I wire J and K together, what happens is I'm wiring J and K together. What happens is I'm calling the JK connected together T. If this happens, I will no longer have this situation. I will no longer have this situation, right? Because J and K are tied together and therefore they cannot be different. Okay, if I put an inverter between them, that's back to the D flip-flop. But now I'm not putting inverter, I'm calling it a T input. Now look at my table here. If T is 0, look at this table. If T is 0, my output is going to be 0 on the clock. If T is 1 on the clock, my output is going to be complemented, Q bar. Okay, that's the 1 case in case of the JK. And therefore, I have a new flip-flop. I call this one a toggle flip-flop. For as long as T is 0, clock doesn't do a thing. When T becomes 1, it toggles. 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0. And therefore, this flip-flop using JK, we created a new flip-flop, toggle flip-flop. Actually, I can create a toggle flip-flop with a D flip-flop, okay? And the D flip-flop taking the feedback and bringing it into XOR. See, now this becomes my T input. If T is 0, the XOR output is always if T is 0, the XOR output is the same as Q. What it means is each time you clock it, Q goes into Q, Q goes into Q, means nothing changes. Okay, but then if T is 1, if T is 1, if T is 1, then the Q output goes through the XOR and becomes Q bar. Okay, Q bar gets clocked into this, Q becomes Q bar, clock it again, Q becomes Q bar. So it goes like showing the timing diagram. Notice each time my clock becomes 0, okay, it becomes 1, then it becomes 0. If Q is a 0, it becomes 1. If it's a 0, it becomes 1. If it's a 1, it becomes 0. If it's a 1, it becomes 0. Okay, that happens for every time the clock sees a 0 after it being 1. So what do I have? My T flip-flop is really a frequency divider. I have 6 pulses on the clock. I have 3 pulses on the Q output. I'm dividing the number of pulses by 2. So this is a frequency divider. We will be seeing more of this later. All right. What else we do here? We also show that we just showed that we can take a D flip-flop and create a T flip-flop. And this is the symbol for the T flip-flop, which is a clock becoming 0. And then clock controls the T. That means if T is 0, clock just puts the Q back into the input. If the T is 1, clock causes Q complement to go back into the output. It's more customary to draw the clock that affects the output after the edge of the clock using this symbol here, meaning it's edge trigger, but it's falling edge trigger. Okay, even though this flip-flop, the flip-flop so far we have seen, they are master-slave flip-flops, and they are not exactly edge trigger. But timing-wise, there is very little difference between the flip-flop that we have here, which is the edge trigger, which is the master-slave, and the edge trigger. Next, we'll be talking about edge trigger flip-flops. All right, so this is the T flip-flop and its variations and a little bit on its timing. Now, what is edge trigger? Let's talk about that.